Okay, in this section, we're going to relate our integrals to the area under a curve. And if you remember from last year, we can use Riemann sums to divide the area under a curve into both rectangles and trapezoids. And they like to give you these problems on the exam using tables, okay? So here is our first example. Here's a table. It says, concert tickets went on sale at noon, we're calling that t = 0, and were sold out within 9 hours. The number of people waiting in line to purchase tickets at time t is modeled by a twice differentiable function L for 0 less than equal to t less than equal to 9. Values of L of t at various times are shown in the table above. So this would be like part A of many questions. We know how these work, but it says use a trapezoidal sum with 3 subintervals to estimate the average number of people waiting in line during the first 4 hours that tickets were on sale. Now, we haven't reviewed this specifically yet, but if you recall, when we talk about average value, you have to multiply your integral times 1 over b minus a. And so if we're going from 0 to 4, if you remember, what that means is that we are trying to approximate the integral from 0 to 4 of L of t dt. And to make that the average number of people, we want to divide or multiply by 1 over 4 minus 0. So we want 1/4 of that value. Okay. Now, the area of a trapezoid is base 1 plus base 2 times the height divided by 2. The height is always going to be the width of your interval, delta x, and base 1 and base 2 are going to be, in this case, it's going to be L of x1 and L of x2. Whatever your function is, those are going to be your function values. Because remember, what we're really thinking of is sideways trapezoids. So we have base 1, whoops, I don't know why I put 2 things there. We're going to have base 1, base 2, and then delta x is the width of our interval, is how that's always going to work out. So our trapezoidal rule is going to be 1/4 times. The first thing that we want is the width of the first interval. 0 to 1 is only 1. Base 1 plus base 2. So it's going to be 120 plus 156 times 1 divided by 2. Plus, from 1 to 3, the width is 2. Our bases are 156 plus 176 divided by 2. And then from 3 to 4 is again just a width of 1, but that's 176 to 126. And we're going to divide that by 2. And so we want to work that out, and that is going to give us the value of our integral, and then we need to multiply that by 1/4. Now, what I see first is that I have a 1/2 that I can factor out of all of those. So this really becomes 1/8 times, this is going to be 276 plus 2 times 156 plus 176, which is 332, plus 176 plus 126, which I believe is going to be 302. And now we just need to add those up and divide by 8. And so the approximate value that I get is, the answer I get is 155.25 people. And it's just people, because remember, the integral of a rate is an amount. That's going to be the average number of people during the first 4 hours. Okay. So I'm not going to work through all of the rest of these because I think we can probably remember well enough how to do this. But let's just remember this next one is also trapezoidal. This one here asks you to use a midpoint Riemann sum. So this wants the integral from 0 to 2.4 of a midpoint Riemann sum with 3 subintervals of equal length. Midpoint means that for the height of each rectangle, we have a curve kind of like this maybe. The height of each rectangle is going to be halfway through the height of the rectangle, or the width of the rectangle. And so the way you find the midpoint is to add the intervals and divide by 2. This one is evenly spaced, so it works really nice. I want 3 subintervals. So this is going to be my first region, and this is my midpoint. And we should double check. Is 0.4 halfway between 0 and 0.8? Yes. My next interval is going to be 0.8 to 1.6. Halfway between there is 1.2. And then similarly, it works out for our last interval. So the midpoint is going to be the width of your rectangle. That's going to be this value here. I take that back. That's going to tell you where to find your height. So these are the height values that we want. So we want that, that's our height of our rectangle right here. That's f of whatever the midpoint is, or v of the midpoint in this case. And then the width is still going to be just delta x. So right here we've got delta x, delta x, delta x, and they appear to be all equal in this case, 0.8, 0.8, 0.8. This is just rectangles, not trapezoids. So to approximate this, we're going to do base times height. So the base is going to be delta x, so that's going to be 0.8. The height we want to use is the midpoint, so that's going to be 11.8 for the first one, plus a width of 0.8 again, times this time a height at the midpoint, which is 17.2, plus 0.8 again, times the height at the last midpoint, which is 16.8. And we put all that in our calculator. Get 36.64, okay? And now, again, using correct units, interpret the meaning. The integral of velocity represents position, or in this case, it's going to be our distance. This turns out to be your displacement. We've heard that word, and you've heard it in physics enough times now. So 36.64 miles is your displacement over the time interval 0 to 2.4. Okay, that's using midpoint as the height with rectangles. We could use the left side as the height for the rectangles. If that was the case, 0 would be the height, 9.5 would be the height, 16.3 would be the height. We could use the right, which would go on the other side, 20.1, 16.3, 9.5. So I'm going to let you look up the rest of these in your notes. Copy those notes down yourself to kind of walk through these different examples, but that's a quick little refresher on our Riemann sums. And there's a couple multiple choice questions at the end that are good, quick practice for you on sort of the AP style of questions. So take a look at those, and I'll see you next time.